Okay, Physics 11H. Let me get the focus lock on here. There we go. All right, Physics H. Sorry. This worksheet 4. We're gonna coming out of the break. We're gonna pick up the pace a bit here, and I'm gonna try to kind of not repeat stuff every day. I'm gonna try to move a little bit quicker on things. I think we can with these units that are coming up here. So anyway. It's kind of just a summary of the friction lab. Talk about it here. Why does material matter? We've talked about this a bit in class, but it matters for a few different reasons. One is when you look at it really on the microscopic level, the smoothness of the surface matters, but that's not necessarily a great indication of why it matters. Also has to do with whether or not the two materials attract to each other electrostatically. Chemically actually. But anyway, we'll go through this pretty quickly, and you can check out the solutions. What I want to get to though is the real meat of it here. Some of these actual calculations here. In the previous video, I did some basic calculations with friction, but I didn't show you this table. So remember, on your equation sheet, it just says force of friction equals the coefficient times the normal force, all right? The coefficient can either be kinetic or static. So when you look at this worksheet, you'll see listed kinetic and static, both of them here. So I gotta just move my phone over a little bit there. All right. Kinetic is when it's sliding, right? Static is when it's at rest. You have to be a little bit careful with the static. So I wanted to just do a couple examples similar to what's on this worksheet, all right, and then you can pick it up from there. If you look at the last video, that'll help explain this worksheet as well. But I wanted to show how to use this table here. So for number 3 here, a 2 kilogram wooden block is pulled across a wooden desk. Determine the force of friction acting on the block. So it's being pulled across a wooden desk. That's very important. So it's moving along the desk. We have a wooden block on a wooden desk. So the surface here is wood on wood. Right there. It's on your reference sheet. We see 0.3 for the kinetic coefficient and 0.42 for the static. So it takes a little bit more to break it free than it does to keep it moving. And these are in the ballpark of what we got in the lab. I think we got like 0.6 something for the vinyl, which maybe is, it's probably something like, oh, I don't know. Yeah, it's closest to actually the wood on wood, right? Or even the rubber on asphalt. So these are all similar to what we got in the lab here. The Teflon on Teflon. If you see static is not listed, you treat it just, it's the same value as the kinetic. All right, this is the case where when they're not listed, that's when, if you did the force versus time graph, we saw a spike, right? Well, if you did one of the more slippery materials, you don't necessarily see that spike. It just kind of goes up and levels off. So if there's no spike, then they're just the same value for the coefficient. But anyway, 2 kilogram block pulled across a wooden desk. Determine the force of friction acting on the block. All right. So force of friction equals mu times the normal force. Now there's actually two problems wrapped into this one, right? Because if we make a force diagram of this, I'm going to get this out of here. We make a force diagram for this wooden block, right? We have the pulling force, force of the pull, force of the friction, the normal force, and the gravitational force, Fg. Right? So those are our 4 forces here. Well, the force of friction, we don't really know what's going on here. It doesn't say if it's a constant velocity or not. It doesn't really matter, right? It doesn't matter what the pull is. We're just trying to find the friction. We know it's sliding, so the force of friction is going to be constant. So it's going to be wood on wood. So again, wood on wood kinetic is 0.3 according to our reference table, 0.3. Then we have to multiply it by the normal force, right? But the normal force here is equal to the force of gravity. So we have to do a little calculation first, determine the force of gravity on the block, right? So the mass of the block, so Fg equals mg All right. The mass of the block is 2 kilograms, 2.0 kilograms, times G, which is about 9.8, or actually, if you just use 10, it makes life a little bit easier. You can always use 10 on a quiz or a test or anything like that. So Fg equals mg, 2 times 10, that would be 20 newtons. 20 newtons of weight. So the normal force is 20 newtons of force holding it up. So the force of friction acting on it, 0.3 times 20 is 6.0 newtons. That would be the force of friction. Now, that's cool. I like it. In the lab, we did at least in one section, which I guess we'll probably do tomorrow with the other section, or we'll do with the other half of the class tomorrow. Oh man, my eraser was not working very well, so I tried using that towel, and it's not working very well either. Yeah, I just cleaned this too with the good stuff, so I don't know what's going on. Maybe I need to shake that spray up. Terrible. Anyhow, alright, maybe it's cold in my garage, and maybe that has something to do with it. But anyway, number 4 is similar to one we did in the video. Alright, number 5. This one's got a trick to it. Determine the maximum amount of static friction. This is a really important one. That will act on the block. Will the 4 Newton force be enough to break it free? Number 6 is pretty straightforward. Let's take a look at number 5 a little more in depth here. 1 kilogram copper block sits on a steel table. So when would you ever do this? Well, you know what, actually, if you have a steel countertop or a steel table, like in a professional kitchen, maybe you have a pot that has a copper bottom, that could be possibly, right? Copper, Cu. Steel is a alloy, right, of iron and, what does that have? Some nickel in it, I forget what exactly. And it's 1 kilogram, so the mass of it is, I'll just write 1 kilogram above it. All right. Pulls on it with a force of 4 newtons. Okay. 4.0 Newton force. Great. Force diagram. Here we go. Force diagram. We label all the forces. Fn, Fg. Fg would be mg. That would be about negative 10 newtons. So this part, we're doing this quick now, right? Fg, mg. 1 kilogram times about 10. It's got to be negative because it's going down. Negative 10 newtons. Normal force plus 10 newtons. All right, we have a pulling force of 4.0 newtons. And then we have a force of friction acting backwards, but we don't know what it is. All right, we don't know what that force of friction is. So the question is, determine the maximum amount of static friction that will act on the block. Will 4 newtons be enough to break it free? So, force of friction, in this case, it's going to be the static coefficient times the normal force. Now, it's important to realize, when you use this coefficient, right, you are actually figuring out the force of friction static max, I call it. It's the maximum amount of friction that can be applied to the object by the surface. All right, the force of the surface object. This is the most it can possibly be when you use this. All right, so let's get that number and see what it is. All right, before we go any farther. So the static coefficient of copper on steel. So you go to your reference sheet here. I got to put this table on the reference sheets I have that I gave you. I'll put it on the back. Copper on steel, static coefficient is 0.53, so that's a really big coefficient, 0.53. That's a nice one. Normal force here, we already calculated, plus 10 newtons. I didn't show this workout very good, Fg equals mg, and we often don't when we do that calculation. We pretty much just, use 10, multiply the mass by 10, make sure it's units of newtons because it's weight. So 0.53 times 10, that's 5.3 newtons of force. Force of friction static max. All right. So here's the question now. Would this object actually be able to be broken free by that 4 Newton force, right? The answer is no. It will not be broken free. So the force of friction acting on the block is not 5.3 newtons. It can't be 5.3, right? If this was 5.3, right, that means this arrow would have to be bigger than this arrow, which means somehow, magically, the friction would be accelerating this block backwards. That doesn't make sense. Friction's a responsive force. The static friction's responsive. It's equal, the force of friction static will be equal to whatever is applied up until it breaks free. Then once it breaks free, kinetic friction takes over, and it's a constant value. So if you think about that graph, right? This is from the lab when we did the force sensor, force friction versus time. Remember, it went up, hit the peak, and then leveled off. So at the peak, that's this value. This is 5.3, that peak. We haven't reached the peak yet. We're like here, 4.0 newtons. We haven't even started moving the block yet. We're on the uphill climb here. All right, we actually got to put in another 1.3 newtons of force, strengthen up our force to 5.3 to get it to break free. Then once it breaks free, it'll start sliding. All right, so we haven't even reached the point where this thing will start moving yet, the 5.3 newtons. That's when you use the static coefficient, you are determining how much force it takes to break it free. The actual force of friction that acts on the block will be simply equal to whatever's applied, because if it hasn't started moving yet, all the forces must be balanced. So 4 newtons to the right, 4 newtons to the left, negative 4.0 newtons to the left. So that's the answer to part C. The force of friction has to be negative 4.0 newtons because no matter what, it's not moving. The force of friction must be equal to the applied force. All right. So if you broke it free now, part D asks us, okay, let's say you could break it free. All right, let's say you could break it free and get it sliding. What then would happen? What would it take to keep it moving? Well, that becomes now force of friction kinetic. All right, so if you could break it free, right, now once it starts sliding, the coefficient of friction goes down because there's no time for those chemical bonds to set up. 0.36 is your coefficient. The normal force is 10 newtons. It only takes 3.6 newtons to keep it sliding once you've broken it free. So once you've broken it free. So the 4 newtons would be plenty to keep it sliding. In fact, if you kept applying 4 newtons, the object would actually have to accelerate because the 4 newtons is bigger than the friction. All right. So that's kind of wrapping up friction for us there. You're going to finish it up. Number 6, number 4. Get those cleaned up nicely on your own. Check out the solutions and submit them eventually here. All right. So that's where we're kind of getting back into action, thinking about forces this week. Force diagram is going to pick up the pace and see how it goes. All right. All right. So have a good one. Talk to you later.